Today we're going to talk about solving nonlinear inequalities. Let's start off with a quadratic. I take x squared minus 2x minus 15, and I want to set that greater than 0. Now, if this were an equality, we'd take and factor. So we know we have x minus 5 times x plus 3, and that's going to be greater than 0. What we really want to know is, does the zero product principle apply? In other words, can we set x minus 5 equal to 0 and x plus 3 equal to 0? It kind of does, but not really. What we do know is a quadratic is going to be a parabola. And in this case, we would have roots of 5 and negative 3. We call 5 and negative 3 not only roots, but we call them critical numbers. And critical numbers are points in which your graph will hit an axis and either go positive or negative thereafter. So if we look at this parabola, and we remember way back from Algebra 1 that if my a term is positive, it's got to go up. So my graph looks something similar to this. What we want to answer is, for what x's do my y's get bigger than 0? Well, where are my y's bigger than 0? Clearly, in the shaded area right here. But I want to know where are the x's that that's greater for. Well, we can see that when x, let's use a better color, x is less than negative 3, that happens. And when x is greater than 5, that happens. Now, if we trace this line all the way out, we know that that happens when x is negative infinity all the way to negative 3, but not including. So in interval notation, it goes from negative infinity to negative 3. Likewise, on the right of this graph, I notice that I'm going from 5 out to infinity. Since the two aren't joined, I need to state I want to look at all of this area in my solution, so I give it a union sign. And that's how we'd answer this. Now, how would you do this without actually having a physical graph? Because some of the equations we're going to be dealing with today and inequalities we're going to be dealing with are not as easily graphed as a parabola. You won't actually know what they look like until later in the year. Well, here's what we do. We take a look at our critical numbers, all right? And in this case, our critical numbers are going to be the negative 3 and the 5. And we put those on a number line and we say, okay, what we need to do is find out what the values of this graph are going to be in 3 different regions. The region where x is less than negative 3, x is between negative 3 and 5, and when x is greater than 5. So what I want to do is find out what my y values are going to be there. And all I'm going to simply do is plug a number in each of these regions into my factored formula to find out what kind of value comes out. If I plug, for instance, f of negative 4 into this factored formula, I get a negative 9 in this case, but I don't care about the number, and a negative, which multiplies to positive. That's greater than 0. Therefore, that's a good thing. Put a little happy face there. All right, if I pick a number between negative 3 and 5, for instance, 0, and plug that into my factored equation, I get a negative and a positive, which multiplies to a negative. That's not good. Okay, that's actually less than 0, and that's not a good thing. All right. Finally, if I plug a value in this region greater than 5, like 6, into my factored equation, I get a positive and a positive, which multiply to a positive, which is greater than 0, and that's a good thing. So what I want to do now is I want to look at, well, what are the values that I need? I need the values that are greater than 0. here they are. And those happen to be the same values in my interval notation. And that's how I take and answer that. Let's move on. So our next example is x squared minus 2x is less than or equal to 3. Notice in this case we have a less than or equal to problem, so that's going to change how my interval notation looks in the end. I'll take set aside equal to 0 just like I do in the equality, factor just like I do in the equality, and I get a minus 3 and a plus 1 is less than 0. I can use, again, my graph as an aid, which I'll do just to get started with. So if I use my graph as an aid, I know I have a critical number at 3 and at negative 1. And I know this has an A term that's positive. So again, my graph rises. Now, I want to know in this case, where are my y values less than 0? Well, clearly we can see less than 0 is under the x-axis. So that's in this region here. Now I'm going to use my test points of negative 1 and 3 and look at the 3 different regions. Below negative 1, between negative 1 and 3, and above 3. Once again, plugging each of those points into the factored form of the equations. So for instance, I will take f of negative 2 and plug it into the factored form. Gets me a negative and a negative, which is a positive. A positive value is greater than 0. I don't want that. Pick a number between 0, in which case I get a positive and a negative, which is a negative. That's less than 0, and that's exactly what I want. Finally, number greater than 3, like 4. Pop that in. Positive times positive is a positive, greater than 0, but that's not what I want. What are the regions that I do want? I want values that are less than 0. Where is that? In between 1 and 3. And I also want to know when it equals 0. So in this case, to state my answer, everywhere from negative 1 to 3, including those, when I plug any of these values into my equation, I will get an answer for y that is less than 0. So since I'm including, once again, I include the brackets. Next example. X cubed minus 16x greater than or equal to 0. Now in this case, you have no experience in graphing cube functions, or most of you don't. So I'm going to go about just factoring this like I would an equality. I have x squared minus 16, which goes to x plus 4, x minus 4. If this was strictly equal to, I'd have 3 roots, which means I have 3 critical numbers, one of negative 4, one of 0, and one of 4. So in this case, I have 4 regions to test. The region less than 4, between, or less than negative 4, between negative 4 and 0, between 0 and 4, and greater than 4. And I'm going to test all those in this factored formula. So I'll look at f of negative 5, f of negative 1, f of 1, and f of 5. Basically, plugging those values in for x. When I plug in a negative 5 to this factored equation, I get a negative, negative, and a negative. 3 negatives multiplied to a negative, that's less than 0. That's not what I want. So that's a frowny face. All right. When I plug a number like negative 1 in, I get a negative, a positive, and a negative. 2 negatives and positive multiplied to a positive, that's greater than 0, and that's exactly what I want. Plugging 1 in, I get a positive, and a negative, which multiplied to a negative, Not what I want because that's less than 0. Finally, plugging a 5 in, I get a positive, a positive, a positive, which is a positive, which is greater than 0, which is the solution I'm looking for. Once again, I want to know where are these values greater than or equal to 0. So where does that happen? Right in this region and right in this region. And since it's equal to, I have to use my brackets again. So I'm going to look, and I go from -4 to 0. Both of those could equal 0, so I'm going to include that. I also have to include the region from 5 out to infinity. But since infinity isn't definable, I put a parentheses around it and then throw a bracket on the 5. Since both have to be included in my solution, I union them. Next, we're going to move from that nasty cubic to a rational expression. These you definitely don't know anything about. However, we do know something about fractions. We know that fractions can never have a denominator of 0. Now, if I were to take and look at this function in its factored form, I notice that x plus 2 and x minus 2 will be in the denominator, which means that if x is equal to plus or minus 2, then the fraction is undefined. Hence, plus and minus 2 are critical numbers. Because the function goes from undefined to something else. You'll see later when we start graphing these rational functions that things will change. Either go from positive to negative or negative to positive for the y values. And then again, things may not change, and you'll see by our test points. X equals 3 would give me a value of 0. So 3 is also a critical number. So what I need to do now is test all of these points. I need to test -2, 2, and 3, because those are all my critical numbers, which again means I need to look at 4 different areas or intervals in my graph. So notice what I'm going to do. Once again, I will take a look at the value at -3, the value at 0, the value at 2.5, and the value at 4. Plugging in a -3, and I'm going to once again plug into my factored form. I get a negative on top, I get a negative and a negative on the bottom, which goes to a negative. That value is less than 0, not something I want. When I plug in a 0, I get a negative on top, negative, positive on bottom, which gives me a positive, which is greater than 0. And that's something I do want to know about. When I plug in a 2.5, I get a negative on top. On the bottom, I get a positive and a positive, which is a negative. That's less than 0. Don't need that in my answer. And when I plug in the 4, I get a positive over a positive and a positive, which is a positive and greater than 0. I want all solutions that are greater than 0. So that's here and here. To state those intervals, I'm going from -2 to 2, and then 3 to infinity. Now, what we need to do is talk about how this is laid out. Notice, at 2 and -2, we said we would get an undefined solution. So I can't include 2 and -2 in my final answer, because if I did, this function would be undefined and it wouldn't be greater than or equal to 0. So I have to parentheses those. For 3, I can include that in my solution because when I plug in a 3, I actually do get a 0 out. So I bracket that. Infinity is undefined, parentheses, and I need to see everything, so I union. Let's do one more, and then we'll call it a day. X over x plus 2 is less than 3. Now, inside, I'm sure you're saying, well, what I'd rather do is make a quadratic out of this by multiplying both sides by x plus 2. Don't do it. And the reason why we're not going to do that is because it takes what was a rational function where we know we have a critical number at -2 and completely eliminates it. And we don't want to do that. We know we've got a critical number. So what we're going to do is we're going to take and set aside equal to 0. Because that's what we really want to know. When is this going to be greater than 0? When is it going to be less than 0? And this is the new problem we're working with. I'm going to get an LCD. LCD is x plus 2. Therefore, my equation goes from x over x plus 2 to -3 times x plus 2 over x plus 2. This gives me x minus 3x minus 6 over x plus 2 is, sorry about that, is less than 0. Given this, I can say that -3, actually -2x minus 6 over x plus 2 is less than 0. Let's get a little more board space. From here, what's going to happen is we're going to identify those critical numbers again. I have a critical at -2. And if you notice his numerator, I'll start working over to the left for a moment. I also find that if x were equal to -3, my function would be equal to 0. So now I'm checking 2 spots. Actually, 3. Intervals between -3 and 2, greater than 2, and less than -3. And I'm going to check all of these values in this factored form of the equation. So doing so, we will go f of -4, f of -2.5, and f of 0. What the heck? So when I plug -4 into my equation, I have a negative from the -2, a negative from plugging in, and another negative. 3 negatives make a negative, which is less than 0, and that's something I want to look at. When I plug in a -2.5, I have a negative from the -2, positive from plugging into the numerator, and a negative from the denominator, which gives me a positive in the end, which is greater than 0. Finally, plugging in a 0, I get a negative from the -2, positive from plugging in the 0 in the numerator, and a positive from plugging in the 0 in the denominator. Gets me a negative overall, which is less than 0. I want to know where my values are less than 0. So in that case, I'm concerned about this area here and this area right here. Therefore, my solution will be from -infinity 2, what my critical number was, negative 3, and from negative 2 out to infinity. The infinities can both be parentheses. Now the question is, can x equal negative 3? Well, to figure that out, you have to look back at your original equation. So really quickly, let's do that because it's no longer on the screen. My original equation says I can't equal. It's strictly less than. So, since it can't equal, we don't include the negative 3. I know the value of negative 2, as can be seen in this fraction here, will lead us to having an undefined fraction. So that cannot be included either. I need to see every value in those two intervals represented, so I union that together. All right? Hopefully this will do you. You'll be able to get through the problems tonight. And if not, you can ask some questions on Monday when I get back. Take care.